Hello, today I am going to present one research paper lifelong domain adaptation via consolidated internal distribution. So paper introduced a method to help a ML model continuously adapt to new types of data it encounters over time even when this new data is not labeled. This approach is useful for cases where the model can't access previous or labeled data to help with its learning. But there are two main challenges: domain shift, which means new data might look quite different from the old data, causing the model's performance to drop, and second is a catastrophic forgetting. As model learns to handle new data, it might forget how to handle the old data. To address this, author propose a method that consolidates internal representation and experience replay, means model saves a small set of representative examples from past data. Here I'm mentioning one real world scenario in which our objective is to help the AI adapt to new unlabeled data over time while remembering the past tasks. What is the scenario? An AI monitor security camera which are installed in a shopping mall. It initially identify common object and activity under normal lighting. Over the time, environment changes, lighting varies throughout the day, seasonal decoration appear, and new product and sign are introduced. The challenge is new domain include lightning challenge and new decoration. So risk is mistaking shadow or decoration for unknown object. So model might be misclassified. Learning from recent images, that is holiday decor, may override our previous knowledge like recognizing regular item or activities. So our AI must adapt to these changes while maintaining accuracy in recognizing object and activity across the all scenario. There are some another example of domain shift like tooth recognition in bright light and a darker light, then weather prediction in a mild climate, and then harsh winter or hotter days. Third one is the shopping trend, which are recorded before 5 years ago. Our goal of continuous learning is to enable the model to adapt autonomously to new data pattern while retaining prior knowledge. What are the challenges in current film method that require large level dataset for new scenario which are expensive and time consuming? UDA, unsupervised domain adaptation, is a type of a learning where a model learns to perform well on new data from a different domain without needing labeled examples from that new data. UDA work by mapping the data from both source domain and target domain to common space. This is called latent embedding space. The process of aligning these two domains can be done in two main ways: generative adversarial learning and minimizing the distance between distribution. In GAN, it is using two network generator and discriminator. These two networks compete to improve each other, leading to better alignment of the domain. And in another approach, it directly tries to make the data from source and target domain as similar as possible by minimizing the distance. But there are some problems in UDA because it assumes that all source domain and target domain are available at same time during training, and it focuses on adapting between one source domain and one target domain. It also retains knowledge from previous domain while still adapting to new ones. This we want from our model. The paper's goal is to bring these two concepts together. It developed a method to allow model to adapt new domain over time, like field, and by also dealing with unlabeled data in this domain like a UDA. Approach handles dual challenge of adapting to new data and remembering previous learned knowledge. They are using cross distance that tells how different our two datasets are in terms of statistical distribution. For example, MNIST has a simple black-white images and SVHN has a colorful complex images. This distance tells us that how much adjustment are needed to make the model from alignment of feature of SVHN to make them look like a MNIST. Uh, to prevent catastrophic forgetting, existing method two approaches: model regularization by retain most important weights and experience replacement. In this approach, it helps the model remembering all tasks by keeping reusing some example from the past. But what is the challenge that model may forget earlier tasks when learning for a new one? What is the solution for memory efficient? That we can use internal distribution and generative experience replay, means generate the synthetic data. For example, in medical diagnosis, a model first learns to detect lung disease from chest X-ray, and later it learns to identify brain tumor from MRIs while generating synthetic X-ray to retain lung disease. The proposed solution is that first train on a source domain, train an encoder to map into input data into embedding space, then map our label source data in embedding space, then fit a Gaussian mixture model and estimate its parameter alpha, mu, and covariance matrix, where alpha is the weightage of each class, then update the model for new target domain. In step, this is the step two. In step 3, it stores a subset of past data, select informative example, and update our objective function as follows. I also mention it appropriate terms with explanation. So, for example, our source domain is a handwritten digit, target domain is a house number, and our goal is to adapt the model from MNIST to SVHN without forgetting how to classify handwritten digits. There are also some error terms which I mentioned in this slide. They are proposing algorithm in which, as I mentioned earlier, first it source the training, then setting internal distribution estimation, then continual unsupervised domain adaptation, and then they got outcome. They validate this algorithm by empirical validation on these four type of tasks in digit recognition. Their source domain is a SVHN and target domain is a USPS, followed by image CLFDA and Office Caltech task. As a network structure, they use VGG16 for digit recognition tasks, and for other dataset, they are using RefNet 15. For evaluation protocol, they are plotting learning curves for 100 epochs. So, in conclude, we can say that better method for estimating internal distribution could further enhance the algorithm's performance. I also conclude whole paper in this slide as a brief points. Thank you.